Okay, I think we can start. So the next talk is response recommendation and automation results from SAPPAN. So this talk will be presented by three presenters, David, Martin, and Mischa. So floor is yours, David.
Great, thank you. Can you see my my screen okay?
Yes, yes.
And hear me okay? Okay, great.
Yep.
Yeah, so thanks. So yeah, I'm David Karpuk from WithSecure. I'll be giving the first 1/3 of this presentation on the incident similarity and clustering technology that we've been developing at WithSecure. So the motivation behind incident similarity is simple. So given a security incident, an analyst would like to get a list of all incidents that are very similar in some sense, to be made slightly more precise in a minute. Why would they want this? So say a security incident comes in and it's not clear immediately how to deal with it. It's not clear if it's a false positive or it should be classified as a confirmed incident. These things kind of depend on the organization, et cetera, et cetera. So a useful bit of contextual information would be how were past incidents treated. If they were very similar, say like, oh, in this organization, such and such type incident is often classified as false positive. There were 5 of these in the past month. They were all classified as false positive by some other analysts. So let me go ahead and say this one's a false positive too. This is sort of the idea. So essentially what we want is a way to measure similarity between incidents. So to get a little bit more precise, I want, given 2 incidents, I want a number, their similarity that's between 0 and 1, 0 being not similar at all, 1 being completely similar. So how am I going to design this function? So we vectorize the incidents, and the similarity is just the cosine similarity between the vectors. So if I have 3 incidents here in my little picture, a red one, a green one, and a blue one, you see the red and the green one are very similar to each other in terms of the angle between the vectors. So I might say that, okay, I have this red incident, I'm not very sure about it, but let me query this incident similarity model and see what the similar ones are. Ah, this green one's very similar. And that was actually a confirmed incident, so maybe I have to dig a little bit further into this red one to see what's going on. The blue incident, because the vectors are not similar in terms of the angle between them, we'll get a lower similarity score to the red one. So I'm of course sweeping all the magic under the rug here. Vectorized incidents is that's the whole game. And I won't go into this, but the magic and the art is all in how you take a security incident and turn it into a real valued vector. So this is our incident similarity technology. It's in production now, being used by our analysts and our customers. And built on top of that is our incident clustering technology. So what do I mean by incident clustering? I just mean that we want to group the incidents together, all of our incidents together, in such a way that within a group, within a cluster, all the incidents within that cluster are highly similar to one another. And what would this do? Well, you could process incidents in batches, right? I click a button and I select all the incidents in cluster 100. If I know that 3 of them are false positives and all the others are highly similar, then I could go ahead and mark all of those false positives in MOS. So this kind of batch processing of incidents is very helpful. And if I could sort of even more exciting is the idea of kind of monitoring the threat landscape over time, right? So if I can track the incident clusters over time, if I can measure kind of how they change, how they merge, how they split, I can say something about the general trends in the threat landscape. And this gives sort of some very like a higher up contextual knowledge to our analysts. And then maybe on a specific basis, I might want to take an incident, find out what cluster it's in, and use all the contextual information provided by that cluster to make a decision about how to process that specific incident. Okay, so how are we computing this? We're using a method called agglomerative clustering. It's also known as hierarchical clustering. And this particular clustering technique is used to guarantee the property that everything within a cluster is similar to each other. So it's currently, the current method of clustering, it's retrained weekly. So every week we take all the incidents in our database and we assign them to a new cluster and we forget everything about the week previously. But in production soon, we'll have a more online streaming clustering algorithm, which takes incidents in as they happen and assigns them to an already existing cluster within minutes of their creation. And this is very close to being finished. It's quite exciting, actually. And this will be of large help to our analysts. Yeah, so what I can quasi demo for you is this clustering system. So let's say I have an incident ID, it comes in and I'm not quite sure what to do about it. And I want to use this similarity and clustering technology to figure out what to do. So I have some incident ID. This is just some unique marker for the incident. And I can load my cluster model. So this is basically essentially a database of incidents together with cluster labels and some other kind of incident features that help contextualize what's going on. I asked the cluster model to tell me about the cluster to which the incident I'm querying belongs, and it will dump out some summary information about the cluster. So I have this incident, I know it belongs to a cluster of size 7. Those incidents happened on these dates and on these organizations. And the cluster is a little suspicious. Of those 7 incidents, 3 of them have actually been confirmed security incidents. So this should raise an eyebrow. 4 of them are unconfirmed, which just means that no human has made a judgment on them yet. So if we dig a little deeper, this cluster is small enough so we can kind of peek into it and see what's going on with the individual incidents. If there were 10,000 of them, we couldn't do this, but there's only 7. So let's take a look at the individual incidents. So this top row, this is the incident that we started with. And then this column here, the similarity to query incident, this is what the similarity score will tell you is the similarity between each other row in the top row. So you can see that you get this 0.86 score almost the entire time, except for this row where the similarity is a little higher. So maybe this one is worth paying a bit more attention to. And as sort of a quasi explanation of the similarity score, we can list kind of the category of detection for all the detections involved in the incident. And this gives you a hint as to why this is a little bit higher than this. So it contains a type of detection that isn't present in the other incidents in the cluster. Okay, so this is a very, very quick demo about how this might be used in practice. So just to conclude briefly my portion, so these technologies support incident investigation by our analysts and by our customers by allowing them access to information about similar incidents. And that access to information about similar incidents helps contextualize things, helps helps give our analysts some broader knowledge of what's going on. And these technologies allow our analysts to track sort of common activities performed by threat actors. And this helps us kind of maintain a high fidelity detection system. So it's helped weed out some detection rules that were firing way too much false positives. Okay, so that concludes my portion. And now we'll go on to Martin.
Okay, hello. We will save some time and will not switch the screen sharing. So I will be presenting the malware analysis automation platform from here. And we can start by introducing the platform architecture on the next slide, where you can see a lot of systems, which I will try to quickly describe. So the whole automation process starts when a human analyst wants to investigate a suspicious file. For example, when a user reports a suspicious phishing attempt or suspicious email with an attachment. So the analysts get the file and needs to do a quick investigation whether the file is a malware sample or some benign file that looks suspicious. So it starts on the left side in the web UI, which is a simple UI where the analyst submits the file. And this is the start of the automation process. When the file is submitted, the systems persistently store it in S3 data storage. so that we have the samples stored. And once the file is in the storage, the Apache Airflow automation platform monitors the storage, and every time a new file is submitted, it starts the analysis process. At first, it uploads the file into the observable evaluator, which is our developed just support tool that uploads the files into Intel our platform, which queries multiple third-party tools for the analysis. You can see examples of the third-party tools on the right side of the screen. I think everybody here knows VirusTotal, Hybrid Analysis, Alien Vault, and so on. So the automation platforms queries all those tools for their analysis about the suspicious file. When the analysis is done, it's passed back to the observable evaluator. And now why it's called observable? Because it's extract all the observables, which are IP addresses or domain names to which the suspicious file communicates, and recursively analyzes those observables through these third-party tools. So the analysis is run multiple times for each observable, and once each observable is evaluated, the results are passed back into the Apache Airflow. The Apache Airflow takes the analysis of the original suspicious file as well as all the observables and creates a PDF report for the analysts and sends it to the S3 storage back to the web UI for the analysts to look at, and also creates the same report in the form of MISP object and sends it to the MISP sharing platform for other teams to use. The final step is the mitigation of the malicious observables. So if we trust the third-party tools enough that they mark the malicious observables accurately, we can block them through the provided APIs on the infrastructure. So next slide, please. So we integrated all this in a tool that can be deployed using one command in Docker. And the only thing that you have to provide for it to work is API keys for the third-party tools, because they usually require some kind of registration for the tool to run. Their API keys are usually free, but you can buy some better licensing for more throughput or more queries per second and so on. So just provide the API keys in the config file and run the Docker. And now we can take a look at how the system will look like once deployed. So next slide, please. So once the tool is deployed, the Airflow starts the monitoring and wait for any new file submissions. Next slide. Here we can see the web UI for the human analysts to upload the file. And next slide, we can see once the file is uploaded, the Apache Airflow starts the analysis process, and we can monitor the progress of the analysis. And once all of this is green, the report is created and sent back to the analysts. So on the next slide, we can see just the simple UI to download the PDF. And on the next slide, we can see the contents. At first, they are the results of analysis about the file sample itself. So its name, hashes, its other file name variants as seen by the tools, and the results whether the sample is malicious or harmless by the third-party tools. On the next slide, we can see the same for the observables, or in this case, IP addresses with which the malware communicated, and the results whether they are malicious or not. In this case, all of the addresses are Google Play Store used by Google to provide application updates. So they are all harmless, but we can see some tools mark them as malicious. On the next slide, we can see the same in the MISP format, which is automatically shared. And the next slide, basically the same. So you can see the observables in the MISP analysis platform. So that was the malware automation analysis platform. On the next slide, we can see the brief conclusion that it's platform independent, and the main usage is that it speeds up the initial evaluation of a suspicious file. So when the human analysts get a lots of file, he can submit it there and then focus on the interesting or malicious ones. So that concludes my talk, and I will pass the mic to Mischa.
Thank you very much. Hello, everybody. Can you hear me good? Well?
Yes.
Perfect. Okay, so welcome to the last part of the response automation section. I would like to take you to a quick tour on what we have been playing with and developing in Dreamlab. Please take us to the next slide, David. As a quick motivation, we know that Security Operations Center analysts are overwhelmed with lots and lots of alerts all around the globe. And we would just like to automate the repetitive, boring things, so the repetitive, boring alerts, and then free up analyst resources to work on the more interesting edge cases and then do actually some threat hunting. How do we aim to do that? In this work, we use the workflow engine. The first, Martin Jarnik talked about the difference between workflow and playbooks. This is actually a workflow, so an implementation of a machine-readable implementation of a playbook. We use those and APIs in the SOC or a CM infrastructure to actually sort of simulate actions of a SOC analyst, at least for low-risk cases. This low-risk cases was a distinction that became necessary because we not only wanted to automate things, but we also wanted to mitigate the risk of doing the wrong thing automatically. So we created a number of different versions of this workflow and thought about what goals we would actually like to achieve with it. And at the end of the day, we realized that we have to distinguish between critical and non-critical assets. So IT assets, clients, servers in your infrastructure. And we basically have two goals with the automation. The first one is that we don't want to act autonomously on critical assets because the risk of disrupting operations is just too high. At the same time, we don't want to miss alerts or just willy-nilly dismiss alerts that involve critical assets willy-nilly, so even if the detection certainty is low. So a simple threshold with the detection certainty will not do. And on the other hand, we would like to automate the treatment of alerts concerning non-critical assets as much as possible. So this is this trade-off that we try to address with the workflow I'm going to show you on the next slides. Please take me to the next slide, David. Yes, so these are the three main protagonists we used in this proof of concept implementation. The first two, the Hive and Cortex, are coincidentally part of Dreamlab's CM solution called SISOC. The Hive is a case management solution. Cortex is an interfacing component between the case management and several external services such as VirusTotal. And then the third party in this team here is Airflow. Airflow is the workflow engine, the same as Martin already showed us in his talk just a few minutes ago. And next slide, please. Yes. So to get a bit of an understanding how this would fit into an organization, we have in a typical SOC very strongly simplified, you have two roles. First, you have a manager of the SOC, and then you have an analyst of the SOC at the very top. The analyst operates or interacts with the CM solution in a SOC, which we've depicted here with the Hive and Cortex. Then you have typically you have one or several detectors on the left side, so the CM solution, which generates alerts. And in our case, these alerts will trigger a run through the workflow that I'm just about to show you. In the middle of all this is Airflow as a workflow engine. This workflow engine integrates with the Hive and Cortex through the APIs I already mentioned. It integrates with an asset inventory, so a configuration management database at the bottom. And this inventory actually contains the necessary information of an asset's criticality. So we sort of invent the notion of an asset's criticality, and we put a number on that. And then finally, Cortex will interact with the asset that is under suspicion that there's something happening there that's not supposed to. Next slide, please. There's a lot going on this slide. We're not going through all the details, but this is the abstracted view of the workflow we've implemented in Airflow and in Python. We already seen a lot about Airflow, so I'm not going to show you the workflow in Airflow again, but this is the decision logic we've created in Airflow. The whole workflow starts at the very left with an alert coming in from the CM or another detection engine. We then start running through and collect some information with the get device info box in the middle from the asset inventory. This includes the asset's criticality that I've mentioned before, and then we have a first distinction where we decide, is this a critical asset? If so, we go up and perform a number of tasks that involve collecting more threat intelligence, and then finally asking an analyst what to do. Yes, analyst what to do. If the criticality of an asset is low, we go below, and then we follow an automatic branch in this whole workflow where everything is finished automatically. In the end, with the diamond 2, there's a decision to block or not block a domain, and at the very end, there's a case update where again through the API, the case in the Hive and Cortex is updated with the most up-to-date information. Please double-click to show these two ways through the workflow. So this is this is what we've implemented in Airflow, which brings me to the conclusion on the next slide. As I said, we've tried a number of different ways of creating this workflow. We've seen some things that work. We've also seen some things that don't work. What did we learn? We have about 2 or 3 pages of musings on why or how things work or why they didn't in the respecting SAPPAN deliverable. The 3 most important ones are here. We can say that automating incident response in this way is really possible, but it does require a good risk mitigation strategy that I mentioned in the beginning. So you really don't want to do the wrong thing, and you also don't want to miss out on things that concern your critical IT infrastructure. The second one is that actually implemented workflows, they have to be use case specific. So in this example, it was a DGA detection to make the connection back to what we've heard from Arthur before. And very likely it will also have to be organization specific, because each organization has their specific ways of dealing with certain alerts and with certain detections. And then finally, the devil is in the detail of the workflow design, not really the implementation. So it turned out the implementation of the workflow actually was the easy part, and then turning and twisting things until we were happy with the outcome overall. And here I mean the risk trade-off that I mentioned before. This took some tinkering and actually quite a lot of work, trying different things and different versions of the same workflow. As an outlook, we can say that we're currently adopting these results in our CM solution. We have this prototype that I just showed you and talked about, and we're currently adopting this into our CM product. And with that, I'm at the end as well of my part. Thank you very much.
Okay, thank you. Thank you for the great presentation. So if you have any question, please try to, you can write it in the chat. Okay, do any question from the audience regarding the response automation and response recommendation? Okay, so I thank the speaker again.